Hello and welcome to HPE ProLiant RL300, the future of cloud-native compute performance. Today's webinar is sponsored by Hewlett-Packard Enterprise and produced by Actual Tech Media. My name is Scott Becker. I'm from Actual Tech Media, and I'm excited to be your moderator for this especially timely presentation. Now, before we get to today's great content, we do have a few housekeeping items that will help you get the most out of this session. First off, we want this to be an informative event for you, so we encourage any questions in the questions box in our webinar control panel. Not only will we have team members responding to questions during the live event, but we'll also have a dedicated Q&A session at the end of the presentation where we'll discuss in greater detail some of the top questions that you ask. Now, that Q&A panel is also the place to let us know about any technical issues that you might be experiencing. A browser refresh will fix most audio, video, or slide advancement issues, but if that doesn't work, just let us know there in the Q&A and we will provide further technical assistance. Now, second, in the handout section of your webinar control panel, you'll find that we're offering several resources, and I'd especially like to call your attention to two resources. There's one link to learn more about HPE ProLiant RL300, and there's a link to learn more about Ampere and HPE. So check those out. Those links will be up throughout the presentation, but I highly recommend clicking on them and bookmarking them now so you don't forget later. Now, at the end of this webinar event, we'll be awarding a $250 Amazon gift card to one lucky registrant. Of course, you must be in attendance during the live event to qualify for the prize. The official terms and conditions of today's prize drawing can be found in the handout section as well. Just scroll to the bottom and you'll find the prize terms and conditions link there. Now, finally, one of the best benefits of this event is the opportunity to ask a question of our panel of expert presenters, and to help encourage your questions, we have a special additional prize for you. That's another Amazon gift card, this one for $50 for the best question. After the event is over, we'll look at all the questions that came in, pick out the very best one, and contact that prize winner. Now let's get to today's important presentation. It's my pleasure to introduce you to our presenters today. We have Karl Szymanowski, who's a Senior Compute Category Manager at HPE. We have Richard McQuaid, a Manager for Engineering Programs at HPE, and Naren Nayak, who's Senior Director of Customer and Developer Engineering at Ampere Computing. We've also got Naren's colleague Vaishali from Ampere, who's going to help us with the Q&A later on. Now, we're having a little trouble here on our end at Actual Tech Media getting Karl's camera up, so he'll just be showing slides, but then Richard and Naren will be on camera with their slides. In any event, Karl's going to set up the event and explain a little bit more about what each of our speakers is going to be discussing. So, Karl, take it away.
All right, thanks, Scott, for that nice introduction, and thank you to our audience here. We know your time is valuable, and we appreciate you joining us today for a lunch and learn around the future of cloud-native compute performance. My name is Karl Szymanowski. I'm a compute category manager in North America for Hewlett-Packard Enterprise, and I'm going to be your host for the webinar content itself. And without further ado, I'm going to just give you a little bit of an overview in terms of the agenda. We're going to cover cloud-native compute performance. That's my segment first. Then we're going to turn it over to Richard McQuaid, who's going to talk to you about open BMC enablement on our HPE platforms. So this is something new, being able to do open standards management within our platforms, kind of an exciting new thing that we're able to provide. Then we're going to transition to Naren Nayak from Ampere Computing, and he's going to talk about Ampere Altra based ARM compute, and that kind of follows along with the theme of our webinar here. So I'm going to hop right into it and start talking about the future of cloud native compute performance. And I want to do this by initially just asking some questions. And those questions are around how your data center works now. What if there was a way to radically change your data center cost model such that you could double, triple, or maybe even quadruple your throughput or your performance? You could reduce your power footprint, or perhaps reduce your physical footprint and reclaim floor space, increase the rack utilization and density. So be able to use more of the rack space that you might not be able to use now due to power or other limitations. And in the process of doing that, overall, you're going to reduce your OpEx. So if you could do all of those things and stay within the similar budget to the systems that you're purchasing today, would you consider it? I think that that's a pretty straightforward question, because if you're increasing performance, lowering cost, increasing density, reducing power, all of those things are goals for data centers. And so the question, or the answer to the question, should be, okay, yes, I would consider it, because that's something I have to consider. So let's take a look at an imaginary data center here with 3 racks in it. So the 3 racks have system A, B, and C in them. And each one of these racks has a 12.8 kilowatt power budget associated with it. So that's kind of a typical number we found in some of the data centers that we've worked with. And the performance of the servers in these racks is approximately equivalent. Now, I don't mean that they have the same number of servers in each rack, but what I'm saying is the aggregate performance with that 12.8 kilowatt power budget is going to be the same across all 3. So you could see the performance here with a spec int benchmark. Now let's extend that and take a look at how many servers are actually in each rack. So rack A has 8 servers, rack B has 14 servers, rack C has 16 servers. So clearly, if lower bars are better, fewer servers are better to provide that same level of performance. Rack A has a clear advantage already. But let's look at now the power that those systems draw. And it becomes even more compelling from a rack A standpoint, because we're only drawing 4 kilowatts out of that 12.8 kilowatt rack budget. But for the other systems, rack B is drawing 7 kilowatts, rack C is drawing the full complement of 12.8 kilowatts. Now remember, the reason we have different numbers of servers and different power draws is because the servers are all performing at a different level, but the performance within the racks, across the racks, is equivalent. Now let's flip it over and say, I want to actually maximize the use of my space in my data center. So I want as many servers as I can to be placed in each rack, such that they can meet my power and cooling budgets within my data center. So now, if we take that tact, System A and System B would each be able to have 25 servers in a rack. System C would be able to have still that same 16 servers that we talked about before. So the maximum number of systems is going to vary. But when we talk about performance, now that spec int benchmark that I talked about in the last slide is radically different now. So we have rack A now having 1.7 to 3 times the performance of the other racks in this comparison. But it gets even more interesting when you look at it from a cloud performance. Now, the title of our webinar is all about the future of cloud native performance in your data center. And so we're looking at cloud performance in these racks. So cloud applications will tend to perform a little bit differently, and the benchmarks around them will be a little different because they are cloud oriented. So what we have here is an average of a bunch of different benchmarks associated with cloud-based applications. And if you look at this one, we're anywhere from 2 to 3 times better in terms of performance on rack A. And that number could vary a little bit. It could actually be higher in some cases, and it could be lower in some cases. But in all cases, rack A is going to outperform the other racks. Again, since this is cloud-based computing, we deal a lot with microservices and containers as part of that design. And so when we talk about microservices and containers, cores become our friend when we're talking about physical cores and the number of physical cores we have in a system to support our cloud native applications. So if we look at this configuration here, what does our core density look like in a particular rack? Well, it's even more compelling than the other comparisons. In the case of rack A, we could have up to 3,200 single threaded cores in the same space that we would only have 500 to 800 of the other system cores. And what that gives you is more capability to have more microservices and containers running at the same time, greater performance, more predictable performance, because we're talking about single-threaded and also constant frequency cores, and I'll address that in just a minute. So when I do the reveal here on the systems, it should be no surprise that I'm talking about a new technology that HPE is coming out in terms of our server lineup, and that is based on an Ampere Altra processor. And in this case, we're comparing an Ampere Altra Max M12830 processor, which is 128 cores, up against a couple of 32 core x86 processors. And you might say, well, of course, these performance numbers are going to be skewed because you're comparing a 128 core processor to a 32 core processor. Okay. My basis for what my comparison at the beginning of this presentation was that the system costs are going to be approximately the same. So if we have one system of each, they're all going to be about the same cost, but the performance and the power draw are going to be very much skewed in different directions. So let me introduce to you my friend, the new HPE ProLiant RL300 Gen 11 server. It is a true ProLiant server built around an Ampere Altra ARM technology processor. It has all of our HPE quality, security management, and support wrapped around it, but it is truly designed for cloud native workloads. And I'll talk a little bit more about that on the next slide, but cloud native tends to be more open source, more Linux, geared toward things like e-commerce, web servers, financial services, as a service type of platforms. And so that is where we target it, because that is where it truly provides the best value and best performance. The RL300 provides more cores, so it provides the best performance per watt of power. And it also does that with a lower overall power footprint. Now, it's important that we mention that these cores are single-threaded, because we're talking about constant frequency cores, which are going to provide a fixed level or a more predictable level of performance. And again, I'll talk to that a little bit more in the next slide. But that allows us to scale the system up to 100% utilization and keep it at 100% utilization while still drawing less power than a comparable x86 platform. So that's pretty compelling right there. And then the last piece here is strategic flexible management. I talked about OpenBMC. Richard McQuaid is going to talk about that in just a minute. And having the choice of using our ILO, which is an industry standard. We set the industry standard for system management with the ILO. But if you want to manage on an open source platform with an open source based management system, you could use OpenBMC, and we have the way to enable that for you. As I mentioned, cloud native tends to be a little different than other platforms and our general purpose type applications. So the Ampere Altra and UltraMax processors are single threaded. We have lots of cores, single threaded, with that constant clock speed providing consistent high performance. And in cloud native applications, there tends to be more levels of inter-process communication or coordination, and therefore the latency and the predictability of the workloads tends to be more crucial. And that's where the RL300 really shines in being able to provide that capability. So we're designed for the highest levels of performance while pulling less power than you would with a comparable x86 platform. The system itself is very simple, a 1U, 1P option with 8 or 10, up to 15 terabytes on the drive. So ample storage capacity, 4 slots for expansion, 2 PCIe, 2 OCP, and then the ability to manage it your way, whether that's ILO or OpenBMC. The two processors that are in these systems are the Ultra Q80 or the UltraMax M128, which provide either 80 or 128 cores. So very high core density in a very attractive price point. But what I want to draw your attention to is those last 2 lines there, which is about power. Typically in your current data center with x86 based platforms, The TDP that's associated with the system determines the amount of power that the processor is going to draw. And in the case of the Ampere processors, TDP really isn't part of that. The TDP is only a small portion of it, whereas we look at usage power, meaning when that processor is under max load, typically it's not going to use anywhere near its max TDP as part of that equation. So that's where we get the power savings. These systems are designed to draw less power and perform better. So in summary on the RL300, the RL300 can deliver real business value for you. Given similarly priced configs across RL300 and x86, you can expect to exceed x86 performance by even multiple factors, draw less power, even with an equally ranked CPU in terms of TDP. You can increase your core density or decrease your footprint in terms of the data center. And you can do it all within the same power budget or power footprint. That helps you reduce OpEx, that lowers your total cost of ownership. That's win-win-win across your data center. Now, it's not as simple as just moving a workload from a current system into an RL300. There is work and investment that's required. And in a few minutes, Narain and I getting from here to there. But it does require you to make an investment in your business in terms of moving those applications from one platform to another. But in the long run, with the way the power and the green data center and sustainability are all playing in our environment these days, that's an investment that is a long-term investment. And to cap it off, just to see how the technology looks, from an overall ARM technology standpoint, it is data center ready. All of these different applications, operating systems, languages, tools, and DevOps pieces, all of them are actually data center ready now. And I believe Narain is going to talk a little bit more about that as well. So it's not something that is a niche piece anymore, a niche product anymore. It can support mainstream data center capabilities. And with that, I'm going to turn it over to Richard McQuaid, who's going to talk to you about our HPE OpenBMC enablement capabilities on our Gen 11 platforms. So take it away, Richard. Thanks for being here.
Okay. Hey, thanks. Okay. Thanks, Carl. I appreciate that. Very excited to be a part of the discussion here with the HPE ProLiant RL300 Gen 11 server. Also very excited to present to you HPE's OpenBMC enablement solution on the RL300. My name is Richard McQuaid. I'm the engineering program manager helping drive the OpenBMC enablement through the OpenBMC program management office here at HPE. So with that, I'd like to go ahead and dive into what HPE is offering from an OpenBMC enablement perspective on the RL300. If you're aware of OpenBMC at all, you're aware that the OpenBMC is a Linux Foundation project, open source project that allows customers who who wish to take ownership of, develop, maintain, and deploy their own OpenBMC firmware across their multi-vendor server environment. Typically, these customers are larger service providers, larger telcos that would have the resources and the open source strategy in place that would help drive that natural next progression in their open source strategy. For HPE's OpenBMC enablement, what we're providing is an enablement path for customers who wish to, again, own that OpenBMC firmware and run that on ProLiant servers. We will be providing that OpenBMC enablement on RL300 in the coming week or two. We're very excited that we are right there signing off firmware and making it publicly available. The our solution provides the capability to securely transfer from ILO to OpenBMC, still maintain the HPE silicon root of trust. And we'll talk a little more about that in the next few slides. Not only do we provide a path for you to go through the transfer of ownership process from ILO to OpenBMC, but there is a path back from OpenBMC to ILO should you decide to re-provision that server in a different role that would require you to place ILO on it as well. And I think it's also very important to understand what HPE OpenBMC enablement is not. What HPE is not doing is we are not developing, publishing, or maintaining an OpenBMC firmware for the ProLiant server. We provide that ownership to the customer. That OpenBMC firmware is your firmware. You want to own it, you want to develop it, and you want to manage that source. So we provide you that enablement path, and then we step out of the way and let you do what you want to do. There is an engagement path, even though servers will come out of the factory capable of OpenBMC enablement. We do want to sit down with you, talk with you, understand your goals, understand your visions around your OpenBMC strategy, and then we will be able to enable you to go through that transfer of ownership process. To talk about the scope of the enablement program, we want to make sure that the customer, you would have the internal resources that would be required for you to properly take on that development, that deployment, and that maintenance of your OpenBMC firmware going forward. You also need to be familiar with firmware security signing processes. This is important because part of that enablement process is signing your firmware image and providing us your public secure key so that we can provide that to ILO, and ILO will recognize your firmware as a valid firmware and thereby maintain our silicon root of trust. Once your OpenBMC firmware is on the RL300, every time you reboot, you would be going through that silicon root of trust process. And that's why being able to securely sign those images is so important to make sure we lock down that security from on your server going to and from ILO and OpenBMC. Our strategy is twofold. It requires changes to two pieces of firmware. One is ILO. ILO will support the transfer of ownership process, but once you've gone through the transfer of ownership process and your OpenBMC image is on the server, ILO is out of the picture. You have to understand, you're actually removing ILO and placing your OpenBMC on the server. The other changes that were required were in the UEFI BIOS. The UEFI BIOS needs to be able to recognize the OpenBMC environment as a valid BMC controller environment. So there were some changes in there to make sure that the integrity was maintained for the server and everything was working well. The good news is that the customer does not have to maintain separate custom specific versions of ILO 6 or HPE BIOS. This support will all be in the mainstream firmware releases for those two deliverables. The process of transfer of ownership for our customers in the OpenBMC image, again, will allow you to go to OpenBMC from ILO and back from OpenBMC to ILO itself. We also have, to help you in your process of of developing, testing. We provide a proof of concept program. We like to work with you, make sure your development is progressing smoothly. You're testing your images on HPE ProLiant servers, so you're building that confidence in the integrity of your OpenBMC firmware, um, and you'll be ready to deploy once your program is complete. To complement that program, we also have an open source tool called a CI build and test tool. If you're familiar with the open source part of this, it is an open source program. We have it in place in HPE. The link below this last bullet here on the slide, you can click on that and link to our OSFCI tool. When you link to that, you'll see that there are Gen 11 platforms that you'll be able to choose from to actually upload your source, run through the build process. Once the build is um, completing properly, then you'll be able to load your OpenBMC firmware remotely onto these servers. You'll have a choice of RL300 and other Gen 11 servers, but you'll be able to actually see your firmware running on the servers. So you will be running your OpenBMC firmware on Gen 11 ProLiant servers. So we make this available from HPE. It is also available as an open source download, so you could download it. You could go out to GitHub and you can download it and install it at your facilities and run it locally. So it would be your choice. This is another option instead of, or prior to loading it on production firmware. It adds a level of safety net, adds a level of expediency to actually get into developing and testing your code. What I've done here is I've taken a few screenshots of what we're providing already in the our publicly available OpenBMC open source firmware that will run on a ProLiant. And again, all this is downloadable from the Linux Foundation's GitHub OpenBMC project. What you're looking at here, this should be kind of familiar. It's like an ILO login screen, but it's an OpenBMC login screen on the RL300. This is what you're going to see once you've uploaded your top of tree firmware and compiled it and you've loaded it on the RL300. This next screen, this is just a screenshot, a quick view of what the system overview looks like today. As you can see, you've got we've got general system information from networking and power and firmware. We're displaying system event logs, the inventory, and LED status as well. On the left over here, you can see there's this general menu. And within those drop-down menus, of course, there's sub-menus that you can go look at. But there's quite a bit of support that's already in our OpenBMC code. This next slide, I like this slide. It's kind of busy, but you get all your different colors for all the different instrumentation for your CPU fans, your PSU input and output, and your general system fans. So again, this is just a general, just to give you a taste of where we are with the OpenBMC support today on the RL300. And I do have additional slides in the back that shows more, that breaks out the submenus on the left-hand side here for you to look at if you're interested. Moving to the next slide and kind of wrapping up, we are, as I said, we're signing firmware off within the next week or two already for the RL300. So the capability is going to be there. Again, we would request that you go through the enablement process so that we can understand your goals, your visions around it, and make sure we're level set on the expectations, both from your standpoint and from HPE's standpoint. Expected launch for RL300 is in this month. Extremely excited about that. That includes support for the transfer of ownership. That'll be on the RL300 Gen 11. And come the end of June, we're looking to round out our OpenBMC enablement support on our remaining x86 servers. Again, full transfer of ownership to and from OpenBMC and from OpenBMC back to ILO, and single ILO firmware and BIOS UEFI firmware. I've included some informative links in the back here for you to look at. These are some links on the hpe.com site that'll give you a further overview of what our OpenBMC enablement process includes, and also the CI test tool, which you can just go to, sign up, create an account, totally free to test your OpenBMC code as you develop it and get ready to deploy it. With that, that would be my overview of our enablement process. Very excited to talk further with you. Go out to hpe.com, search for OpenBMC, and there'll be more information for you there. Just send in a request and we'll reach right back out to you. With that, I'll turn it over to Naren Nayak, and hopefully chat with everybody later.
Thank you, Richard. My name is Naren Nayak. I am part of Ampere's customer and developer engineering team. I'm responsible for ensuring that customers, partners, and developers get the most out of Ampere's silicon products through various activities like software porting, optimization, and developer outreach. I'm thrilled to be here today to talk about the HPE ProLiant RL300 Gen 11 platform powered by the Ampere Altra family of processors. And I'm going to add a little bit of color. My agenda here is to add a little bit of color to Carl's statement around the changes that one needs to make to transition from the legacy x86 processors based platforms to an Ampere Altra based platform. Carl has spent a fair bit of time talking about the values of the platform. I'm here to double click on how do you actually make the transition. So consider this to be a sort of playbook of sorts to transitioning from x86 based compute to Ampere Altra ARM based compute. Let's start with the highest level, right? At a high level, how do you approach this problem? You've got a large infrastructure and you've got a variety of applications, all the way from legacy applications to cloud native stacks that are running in your infrastructure. Trying to move all of those to a new architecture is not straightforward. It's not easy. It is a once in a lifetime opportunity as well as a once in a lifetime sort of an endeavor. So it needs to be planned well. At a high level, there's 5 steps that we recommend. Learn about the technology first, assess, build out your solutions, test and optimize, and then eventually leading to a deployment. So let's start with learning about the Ampere Altra processor. Carl actually talked a lot about some of the technologies here. Let me provide a little bit more detail here, right? Altra is the world's first cloud-native processor. Where you would ask, what's a cloud-native processor? Simply put, it's a processor that runs cloud-native applications. These are applications that are born in the cloud. They're typically designed to take advantages of features like scalability, elasticity, high performance. So those are the core tenets that we had in mind when we designed the Ampere Altra and the Ampere Altra Max. So some of the things that we've designed in there are designed to be sensitive to developers' pain points around programming, deployment. Let's start with a few examples. On the left, you see what is typical of the incumbent legacy infrastructures. chances are most of your hardware in your data centers behaves in this manner. You have multi-threaded cores, you have operating frequencies that are best effort. The processor will try to maintain a frequency the best they can, depending on the thermal constraints. There's limited core counts, and then you have smaller private caches because more die space is dedicated to sharing across applications, which is typical for legacy type applications. In today's world with cloud native applications like microservices, like Carl pointed out, there is a fair bit of sharing that happens between microservices, and there's multi-tenancy in the cloud. So we believe in a slightly different approach. We start with single-threaded cores. There is no simultaneous multi-threading or SMT. I'll get into that in a couple of minutes. Carl mentioned we've got consistent operating frequencies. You'll see the effect of that. Maximum core counts, we're actually designing this for a scale-out infrastructure. So if your code is modern enough that you can take advantage of core count and more platforms in a scale-out manner, then the Ampere Altra processor works beautifully. We've got larger, low-latency private caches. We believe in private caches that are closer to the cores, so they're much faster, and using our die space in that manner. So all in all, high performance, power efficiency, scalability, and predictability are sort of our 4 core tenets that we use to design the Ampere Altra with 80 cores and the Ultra Max with 128 cores. Let's move on to assessing your options. The easiest thing to do is to start with an inventory of your software stacks. This is, it's not as simple as it sounds, but typically one would start with operating systems. We would recommend you start with operating systems because that's where it all begins. You're very close to the metal. If your operating systems do not support, ARM-based architecture, ARM64 architecture, it's very, very difficult to build applications on top of that to support the new architecture. So as you can see here, commercial as well as community built Linux distributions, all the way from Red Hat and Ubuntu and SUSE to Debian, CentOS, even Rocket Linux and Alma Linux they support the ARM64 architecture out of the box and as a first-class citizen. Right? We would recommend, and you will see this theme throughout, we will recommend newer versions because the ARM architecture has software on the ARM architecture has improved tremendously over the last 5 years and continues to do so. And there's rapid movement in the maturity, the performance, and the feature set that's available with newer versions. So we would always recommend using newer versions of operating systems and everything else you see in this presentation. Moving on to compilers. Once you've got your operating system story kind of, if you've got that box checked, all of your software needs the right kind of build environment and the right kind of support for ARM64 to move applications over. So most open source software stacks support them natively as well as the compiler. So if you look at GCC, if you look at the LLVM compiler infrastructure, if you've got compiled languages like Go and Rust, these support ARM64 as a tier 1 platform, as well as runtime and interpreted software stacks and compilers are actually a lot easier. Runtimes like Java, .NET Core, and Python support ARM64 out of the box. We are very, very close partners of Oracle in ensuring that the Java virtual machine and the JDK support ARM64 out of the box and in a performant manner. And we do the same with the .NET teams at Microsoft. As I mentioned, newer versions will generate more performant code. Moving on to applications. Now, this one is not as straightforward as operating systems and compilers and runtimes, because you've got applications that have been written over years, maybe decades. You've got different programming languages. You've got different types of applications. what type of applications should you use the RL300 Gen 11 platforms for? At a high level, what is easiest is applications that are written in runtime languages. These are languages like Java, Python, .NET. These were designed to be written once and run anywhere, right? So those are applications that will move very seamlessly to be able to run on these platforms. Open source software stacks like in-memory caches like Redis, Memcached, open source databases like PostgreSQL, MySQL, big data and analytics frameworks like Hadoop, Spark. These have been tried and tested on ARM64 architecture, so they will work very well on the RL300 Gen 11 platforms. And then finally, as I mentioned, these processors were designed for cloud native and scale out workloads. So things like web workloads, your Nginx's, your Apache web servers, these will run out of the box. These will run very, very well on the Ultra-based platforms. So general rule of thumb, newer versions and a cloud-native software environment make for a much easier transition. Okay, so where should developers start? Now you've got all of these applications. You've done an inventory of the applications. Where should you start? Okay, so there's 3 different vectors that you want to look at. Right? One is the amount of effort you need to put in. Software that has ARM64 support today, hey, that's low-hanging fruit. You should start with that. Something that has a meaningful footprint, right? Something that has an impact in your data center. If you've got 1% of your data center running a specific software stack, chances are it's not worth moving that thing first because the overall impact isn't going to be as much. And then finally, value, right? If you've got software that can benefit from cloud-native processor features, hey, that's something you should start off with. So we would recommend starting off with low-hanging fruit, looking at the intersection of the 3 of these, the effort, the impact, and the value, and starting with those applications or those application software stacks. Let's take a few examples here. Let's say you've got a large Java or Go or .NET application in your infrastructure, running some software like, I don't know, something like Hadoop, that's 40% of your infrastructure. And that can benefit from more cores and machines. That's a big thumbs up, right? That should be a lot more straightforward than some applications that I'll get to in a few minutes. Let's say you've got an Nginx cluster, and this is your main web server, your web front-end server, and that cluster is about 30% of your fleet. Okay, that's an easy one, relatively speaking. That's been tested. Nginx is one of our main applications that we start off with. You can replace Nginx with Redis, Memcached, any of the open source software stacks that have been developed over the last couple of decades. Those will run fine. Let's say you've got a custom video encoder with 3 million lines of code that was developed 10 years ago and has hand-coded Intel assembly instructions. Well, that takes a bit more effort, right? We would recommend you not start with something like that. So the takeaway I want to leave you with here is migration is not an all or nothing proposition. You should start off with small POCs with certain applications that are impactful and provide value to you. And then you can move the rest of your stacks if you choose to. Now, one thing I want to point out here also is the interoperability between the different architectures. One of the things that has happened over the last decade or so, from a programming paradigm point of view, cloud native, among other things, also means that these are built to interoperate with other architectures, with different programming languages. Here's an example. With microservices, you technically do not care which languages the individual microservices are written in, as long as they can talk a common language, as long as they have a contract that they can adhere to, it does not really matter. So that really makes this entire paradigm architecture agnostic. And so we have examples in our labs where we've got clusters of x86 servers running workloads like Ceph or Hadoop where part of the cluster is x86 and the other part is ARM64 based Ultra compute. And it works out of the box because that's part of the software magic. All right, let's move on to building. How difficult is it to build my application? This is one of the most common questions we get from developers. It depends, right? It depends on the size of your application. It depends on the programming language, like we talked about. Something like Java, a lot more straightforward than other programming languages. It also depends, like I mentioned, on architecture-specific optimizations you've got in code. If you're the kind of developer that likes to be very, very close to the metal and has assembly instructions in your code, that takes a bit more effort. So let's look at an example. PostgreSQL, in case you don't know what PostgreSQL is, it's an open source relational database. It's among the top 5 databases in use today. And it is a large, complex application. It's been deployed at scale by a lot of companies. This is one of the most popular RDBMSs that we get questions around these days. Well, what does it take to build this on an HPE RL300 Gen 11 Ultra-based platform? Let's take a look. Right? It takes 5 lines of code. Right? All I'm doing here is cloning the Postgres repository. I'm building it. I'm not even building customizations for code specific to Ultra with optimization flags in the compilers. I'm not doing any of that. All I'm saying is, build it for the native platform. As long as you build this on an Ultra-based platform, it'll have all the right optimizations. The compiler will ensure that it has all the right optimizations for that platform. And that's all it takes, right? Now, obviously, testing it, unit testing your code, all of that it still exists. You have to do all of that. But, I would guarantee that 10 years ago, you could not do this on any ARM-based platform. One of the most common things we've heard from developers when they first use an ARM-based compute like Ultra is it just works like all the other platforms I've used over the years. And that's sort of the best compliment for us. It basically means things are working out of the box, which is exactly what we've intended all along. So find more transition and building guides and tips and tricks on developer.amperecomputing.com, as well as the HPE site on Ampere Computing. All right, let's move on to optimization. Right, optimization is you've ensured functional correctness of your applications. You're able to run them on the ARM infrastructure. Now you want to make sure you squeeze out the last ounce of performance from the platforms that you've paid for. Performance tuning is not just a science; it's also an art. There's a small group of people in the industry who can do that. But the tools used are exactly the same as on an x86 platform. If you're used to tools like perf, systat, eBPF, all of those will work out of the box. Ampere has put in a lot of effort to ensure that all of our goodness from performance tooling, performance monitoring units, all of that has made its way into open source stacks. There are some things to be aware of, and these are good things, not bad things. Carl talked about all Ampere cores being real cores. What really does that mean, right? So on the left, you'll see multi-thread x86 cores here with a technology called simultaneous multi-threading that was put together probably 20 years ago. Actually, it predates that, but I think Intel made it really, really popular 15 years ago. And that's basically a way to make one core look like two to the operating system. So you can run multiple applications. So in this case, you're running a database and an AI workload on two of these, what looks like cores, but are really threads. And so underneath at the microarchitecture level, these are sharing resources, right? They replicate the register state, so they look like real cores to the operating system, but underneath all the caches, the execution engines, these are all shared. Now, this kind of technology works very, very well on laptops and desktops, not really on servers, and definitely not in multi-tenant environments. On the right side, you'll see single-threaded cloud-native cores like the ones Ampere has built. Each of these cores is a real core. So all the way from the register stack to the caches and the execution engines, each core has its own resources that are private to itself. And so that makes it a lot more resistant to noisy neighbors and makes for more predictable performance. Carl also mentioned there were no turbo frequencies. Actually, I think what he said was there were consistent frequencies. This is what that really means, right? There are no opportunistic turbo frequencies on Ampere Altra processors. And opportunistic turbo frequencies allow you to ramp up frequencies of your CPUs in lightly loaded scenarios. So if you're using just one core on your laptop, you would love to get 5 gigahertz. Well, when you're using all the cores on your laptop, you're not going to get that because there are thermal constraints. On servers, these are designed for higher utilization. You do not want to buy a big server to run 5% loads throughout. I would hope you wouldn't want to do that. So if you are trying to push your utilization up to higher levels, then you want consistent frequency. So what you see here is a SpecInt that's run on 2 platforms. It's run on an Ampere Altra Max platform as well as an AMD EPYC Milan platform. The down spikes that you see are the individual SpecInt workloads completing. So that is expected. And what I'm looking at here is the frequency. And so you can see that on the Ampere Altra Max, it tries to and succeeds in maintaining 3 gigahertz. That's 3 billion cycles a second consistently throughout the workload. Whereas the x86 server has trouble keeping up from a frequency point of view because some of these workloads are very power hungry and they hit the thermal limits, and that forces the processor to pull down the frequencies. And then third, apps will scale to higher loads. What you see here is containerized media encode instances, and as you increase the load, around 50% or so, the x86 servers, because they've run out of cores, they're now relying on hyperthreading or SMT, and you will see the curve bend because there's contention amongst the different containerized instances. Whereas the Ampere Altra can continue scaling. It was built for scalability. So the takeaway really here is, if you're used to targeting 20, 30, 40% of utilization as your sweet spot in your production infrastructure, that can change with the Ampere Altra based compute. You can push your utilization, your loads much higher because these processors were built to give you better performance at the higher ends of the load line. All right, let's finally talk about deploying. Deploying is probably one of the easier steps here. And this is basically making changes to accommodate multi-architecture because you've got an entire fleet that is likely x86. As you start introducing the RL300 type compute, you want to make sure that they interoperate. And so most of the cloud native paradigms allow for multi-architecture deployments. All you need to do is update your infrastructure as code tools like Terraform, Ansible. For containerized environments, use something like Docker image manifest lists. An example is given below where you've got a Linux AMD 64, that's an x86 server a deployment, as well as an ARM64 container repository, and these can coexist. If you don't, we would always recommend canary deployments to ensure functionality and expected performance. This is where you would divert some of your traffic onto a test cluster to see how they would perform functionally as well as from a performance point of view. And when you're satisfied, you can switch that cluster over to your production environment. All right, let's recap. You want to start by learning about the technology. You want to do a detailed assessment of your software stacks, study the type of applications, make sure that these support ARM64 or AR64. You want to start building certain applications. We talked about the criteria that you can use to choose the types of applications. in general, build with newer versions of compilers, use the latest versions of applications if you can, test and optimize, validate against your usual test suites, use the performance tuning guides on the Ampere Developer Center, and then finally deploy, perform canary deployments, and study your performance and reliability under load. Carl talked about the expanding software and provider ecosystem we've got, all the way from operating systems to applications. These are all the things that are tried and tested. These are some of the most common software stacks that our customers ask us about. And what do we do with all of this? Well, we've got a web page where you'll see a dashboard for Ampere-ready software. So we plug all of the stacks that you see on the previous page into a regression framework where at this point, we're looking at functional testing, and we're rapidly adding performance testing to this. So on a nightly basis, across all of these platforms, all the way from Ampere's bare metal platforms in our labs for Ultra and Ultra Max to the public clouds, as well as now you see the HPE RL300 platforms being stress tested on a nightly basis. And you see a dashboard here with the results of all the smoke tests that we run. All right, I'm going to leave you with a plug for the Ampere Developer Program. This has been very helpful for our customers in the past. It's developer.amperecomputing.com. It's a website with curated content, lots of tips and tricks to deploy, optimize on Ampere products. You've got a developer newsletter that you can sign up for, and lots of sample code and documentation. So at this point, I'm going to turn the mic back to Carl. Thank you.
All right. We've got a poll question here for you about which additional resources you'd like from HPE. So we'll leave that up during the Q&A here. But Carl and Richard and Vaishali, are you guys ready for some questions?
Absolutely.
All right. The first one we've got here comes from Brandon, who's wondering how does HPE ProLiant RL300 Gen 11 leverage the cloud-native architecture and capabilities of Ampere processors? So, we heard a lot there from Naren about the capabilities of Ampere, and anything about the way HPE leverages those.
Well, clearly HPE is the first into the market to support an enterprise class ARM processor, and so we've designed a system with a highly optimized platform to take advantage of the actual data center needs in terms of the Ampere processor. So this is a ProLiant server exactly like the rest of our ProLiant server line, meaning it is every bit a mainstream high performer as any of the other servers in our environment, but providing that processor with the single-threaded cores, high performance for cloud-native workloads.
Okay. Yeah, super. We have another question here from Sergey, who's asking, how do you solve a challenge in redeploying applications which use x86-based binary files? Does that require some special attention?
Yeah, I could talk about it a little bit. In general, yes, if it is x86-based binaries, we would have to recompile it for ARM64 because of the endianness and different instruction set that x86 supports versus what ARM supports. However, if it is a small application and maybe if the performance is not that important to you, there is also x86 emulator, Box 64, which can be used to run x86 binary on ARM architecture. So that's another possibility as well here. But you get the best by recompiling the source for ARM architecture.
Okay, excellent. We had a question here from Valentino that I think that I think that really Naren answered this pretty well. He was asking, what's the problem with cloud native performance? Valentino, maybe follow up if there's specifics, but that question did come in just before before Naren really went through that. And I think looks like we're go ahead.
Yeah, I can elaborate a little bit
Okay.
on what Narain said. The problem with cloud native performance, I think it's more about the problem with what's the existing platforms can support for the cloud native applications. What cloud native applications demand is low latency and scalability. If you think about cloud native as microservices, they need to be able to scale with more number of cores and predictability, which is what Ampere CPUs offer. I think it's more about the platforms or the CPUs that exist today. Can they support cloud native performance?
Okay. Yeah, Vishali, thanks for that. Thanks for that additional context. Appreciate it.
Thank you.
Well, I think we're about on time, but Carl, just if somebody wants to get started, with HPE and these RL300s, any steps that you'd recommend?
I would certainly recommend going to our HPE website and investigating the RL300. You did post a link there earlier, and the RL300 is really in a unique spot to provide much higher performance with lower power draw. So again, those things I emphasized at the beginning, increasing your density, increasing your performance, lowering your power footprint. Those are all very compelling things, especially in today's world where we're all trying to be a little bit greener, having a more sustainable attitude. And so start out on the HPE website there. Thank you.
Okay. Super. Well, Carl, Richard, Naren, Vishali, thank you for putting together a really informative presentation and for your insights here in the Q&A. Really appreciate your time today.
Thank you.
Thank you, Scott.
Thank you.
And before we wrap up, we do have one more piece of business. It's the Amazon gift card prize drawing. And the winner of that gift card today is Brad Bush from Hawaii. So congratulations to Brad. We'll be in touch to get you your card. And with that, on behalf of the Actual Tech Media team, I want to thank Hewlett Packard Enterprise for making this event possible. And thanks as always for attending and for your great questions. That concludes today's event. Have a fantastic rest of your day.